Okay, Assalamu alaikum and very good morning to everyone. Can you hear me?
Yes, can hear, yes.
All right. Okay, thank you everyone for attending this seminar today. Today we are going to have our MRG talk series, microwave research talk series. And my name is Abbasi and I'm from Faculty of Electrical and Electronic Engineering Technology, Universiti Teknikal Malaysia Melaka, UTeM. Okay, so today I'm going to share about my research. It will be just a sharing session about the reflectarray antenna for modern day applications. So what I've been doing in the past few years about the reflectarray design and analysis, I will be sharing today. So if we will have a question and answer session at the end of this talk, but if you have any question during the session, you are welcome to stop me and we can discuss at any point about anything. All right. So basically, when I mention about modern day applications, you know that modern day applications can cover a lot of applications. So basically, we can go for 5G, 6G communication systems, application like that, and other application like X-band application for radar, extraterrestrial communication, and other things. So for this presentation, I will be discussing about these two things, that we have designed reflectarrays for X-band and also for the millimeter wave frequency range. All right, so today we will be covering about the introduction of the reflectarrays, what are the basic of the reflectarrays, the background of the reflectarrays, and then we will discuss about passive reflectarray design and analysis, some basic steps of the design and analysis, and then about active reflectarrays at X-band frequency range. So I will share about our design that we did for active reflectarrays in X-band frequency range using electronic components. So when we talk about electronic components, we can use different type of components like MEMS switches, we can use spin diodes, we can use varactor diodes and others. But here we will be discussing about the pin diode designs. And also for the tunable materials, we can also design active reflectarrays using tunable materials. So when we talk about tunable materials, we have different options. We have option like graphene, we have liquid crystals, we have other tunable materials. So in this presentation, I will be also discussing about tunable materials design based on liquid crystals. And finally, we have a millimeter wave frequency range design for the reflectarrays, for beam steering reflectarrays based on the mechanical rotation of the array. So we will see about that as well in the end of this talk. All right, so before going into the details of reflectarrays, how they evolved from where they came. Okay, so if we know that in the 1880s and 1900s, the development of the different types of antennas had already started before the World War II and World War I. So in the start, we had parabolic reflectors, which were bulky structure. Of course, we can get the high gain from the parabolic reflectors, and the problem with them is they use the mechanical beam steering. When we want to do the beam steering for application like radio astronomy or extraterrestrial communication, we have to do the mechanical rotation of the whole of this structure. So that becomes very tedious because we need to rotate the whole of this bulky structure. And of course, they were low cost or moderate cost, and they have some design complexity when it comes for the beam steering. So then there were in 1900s, in 1905, the phase array antennas were proposed, which were the planar structure. So with the planar structure, they were easy to be integrated on different type of surfaces, planar surfaces, and they can be used for military communications. All right. And then for beam steering, instead of mechanical beam steering, there was electronic beam steering that comes that uses different types of electronic components for transmit receive modules and also the amplifiers and other electronic components. But with all these components and the beam steering, the design becomes complex and it becomes high cost as well. So in 1991, the reflectarrays were introduced, the microstrip reflectarrays were introduced, which had the advantages of both the parabolic reflector and the phase arrays. So they were the planar structure like the phase arrays, and they have high gain as both parabolic reflector and phase arrays. And they in the passive reflectarray, there was no beam steering, but in active reflectarrays, we can have beam steering. Okay. And then because they were designed on a simple PCBs, so they can be low cost and simple to design. But when we introduced the active planar reflectors, or for the reflectarrays, we had to integrate the electronic components like MEMS and MEMS switches, pin diode, varactor diodes, other things. So that becomes slightly complex, but still it is less complex as compared to phased arrays. Okay, we will see more about the design of this type of reflectarrays. Okay, so for when we talk about the modern day application, we know that for modern day application, we need to optimize the performance of the antenna based on their gain, the efficiency, bandwidth performance, and the beam steering is very important, and also the polarization. Okay, so we need to have the multiple polarization or different types of polarization for the antenna. So these are the important components, important performance parameter that we need to look into modern day applications. So that's why we investigated different types of design for reflectarray that I'll be sharing today. All right. So basically, how a reflectarray works, it's a planar surface. It consists of microstrip patches that are shown here, and they are printed on a dielectric substrate or a simple dielectric substrate and backed by the ground plane. So we have a feed horn. Same like the parabolic reflector, we have a feed horn placed at a certain distance, and then we have input from the feed horn, and then the electromagnetic waves are reflected back from this reflectarray. So this part over here is the reflectarray, and this is the feed horn antenna. So what we aim is that we can get a planar wave after the reflection from the reflectarrays. So how this convert this spherical wave into a planar wave, it depends on these microstrip patches. So we have different types of options for the microstrip patches. For the basics design, we can have patches of different sizes. Okay, we can have simple rectangular patches of different sizes. We can have patches of same size but with different stub sizes or with rotation of different elements. So by doing these simple things, we can modify the phase of each of the elements. So by modifying the phase of each element, we can modify this incident wave, and we can make a reflected a planar wave in front of the reflectarray here. Okay, so these are very basic design, but currently there are much more advanced designs that are used by different researchers. Okay, so this is very basic animation of how the importance of beam steering as compared to mechanical, as compared to parabolic reflector. Let's say when we want to target a satellite, okay, for satellite tracking, where for the parabolic reflector, we have to move the whole bulky structure of this antenna. We have to move it from one end to the other end using mechanical motors. So this becomes very tedious. So in reflectarrays or in planar reflectors, what we can do it using electronic components. So when we use electronic components, we use a power supply, and we can modify the phase of each element, and we can steer the beam based on our requirement for the tracking. So this is basically the basic concept of why we can use reflectarrays as compared to parabolic reflectors. Okay, so when we talk about the applications, basically reflectarrays can be used in all the applications, or in most of the applications which currently we are using parabolic reflector and phase arrays, as they have all the qualities of these two antennas. So they can be used in civil and military radars, can be used for Earth observatories, space and extraterrestrial communication, weather forecasting radars, satellite communications, 5G and 6G communication, etc. So we can cover a lot of applications under these reflectarrays. All right, so when we talk about the design, we have two-step design of a reflectarray. So we have a unit cell design and we have periodic array design. So basically, when we do a unit cell design, we design different type of configurations, and we design it as an infinite array. So when we use the simulators like CST or HFSS, we can use the boundary conditions, and we can make this single element as an infinite array. So we do all the analysis based on most of the analysis based on this array, based on this infinite array, which is actually a unit cell design. So it doesn't take too much time in CST or HFSS. Okay, and then we can see the reflection loss and reflection phase curve, and we can do the analysis based on these two curves. Okay, so once our design is finalized, the unit cell design is finalized, we go for the periodic array. So for periodic array, we have to do the progressive phase distribution for finite array design. We have to make sure that we place the elements in such a way that we can get the reflected beam as we desire. And then we do the analysis based on the radiation pattern. But when we design the periodic array, let's say in the software like CST or HFSS, we cannot use it. That takes a lot of time. The simulation and design process takes a lot of time. That's why we do most of the optimization based on our unit cell, so that we can save the time and we can also save the memory of our PCs. Okay, so coming to the unit cell design, just sharing some of the fabrication and scattering parameter measurement that we had done for our unit cell. So we start with the simulations. Okay, this is for CST and this is showing the HFSS. So we design different types of elements as shown here. Rectangular patches with slots, with circular slots and different types of slots. And we design it in CST, and we have a waveguide port at a certain distance from the our unit cell. This is our unit cell, and that is there's a fully ground at the backside. And then we use this type of boundary condition, magnetic and electric walls. We create magnetic and electric walls with this element, and then by using this magnetic and electric wall, it will become an infinite array. So it will give us the response of an infinite array by just using the boundary conditions. So we can do the simulation very fast and we can get the response of the infinite array. So from there, we can finalize our design. We can optimize our design, whichever we want to use based on surface current distribution, electric field, and all the things. And then we can go to the periodic array design. So similarly, we can do same thing. The infinite array design, we can do same thing in HFSS using flow quad port and master and slave boundary conditions as shown here. So once the design is finalized, okay, so here we have finalized our design based on boundary conditions. So when we want to do the measurements, because after doing the simulation of unit cell, we have to do the measurements also for the unit cell. But in simulation, we are doing it for the infinite boundaries, for infinite array. So when we want to do it in measurements, we have to create a waveguide. So this is a waveguide that we created for X-band. Okay, so on one side we have standard X-band dimensions that are like this. Okay, this bigger dimension and the smaller dimension, and the E-fields are excited in this direction. And the other side we have this dimension of our unit cell based on the half wavelength dimensions. So we have to insert our unit cell here, and it will become an infinite array, or it will give us the scattering parameter measurements of an infinite array. So this waveguide we designed using CNC machines in our university as well. Because this is not a standard waveguide, so we cannot use a standard waveguide because this is tapered in both X and Y direction. That's why we have to design it by ourselves. Okay, so we fabricated different types of unit cells. Okay, these are different types of unit cell design based on different configurations, and then we did this scattering parameter measurements. Okay, there's a vector network analyzer connected with this waveguide. Okay, through a cable, and there's a coax to waveguide adapter connected at the back side here. So this is the standard size, and this is our unit cell design. So we insert one of this unit cell design at a time on this side, and we can get the S11 result for our unit cells. So these are the reflection loss and reflection phase results for different samples. Okay, with different dimensions of these slots, we got the different results. So this is one sample of the results. So we can see a very good agreement between the simulated and measured results. So one thing I want to highlight here is that for this type of reflectarray or reflectarray unit cells, we are not aiming to have reflection loss below -10. Okay, we are aiming to have it as close to 0 as possible, because this is a reflector as compared to a patch antenna, microstrip patch antenna, that is a radiator. So for that case, we aim to have it at -20 dB or -30 dB. But for this case, we are aiming to go as close to 0 as possible. So still, this is very high loss, but it is based on all the measurements. So we got good comparison between the simulated and measured reflection loss and reflection phase curves. So why we have different dimensions of our design here is that because let's say if we choose this design, So this is one sample of circular slot. So we vary the radius of the circular slot so that we can have different phases. When we want to design the array, we need to have elements with different phases. So this is how we get the different phases. And then we can see that it is covering a good phase range, okay, a dynamic phase range of 346 degrees, which means it is covering, if we design at 10 gigahertz, we can cover from 0 to, let's say, up to 346 degrees. So the rest, ideally, we want it to be 360 degrees, but it is covering up to 346 degrees. So the rest is the phase errors. Okay, so these are the elements that we can use for the periodic reflector array designs. Okay, so after the passive elements, we tried to design with the pin diodes based design for the switching. Okay, so we used MACOM MA4GP907 pin diode, okay, which has series capacitance and series resistance as given, and then we just inserted the pin diode in the gap here. Okay, so we have a slot and we have a gap here to have two different potential for the pin diodes. Okay, so we inserted the pin diode here and we switch on and off this pin diode, and we can see that we got the frequency switching. Okay, so this is the measurement setup for the pin diode based design. So we have the same design. We have vector network analyzer connected with the waveguide, and this is our pin diode based design. Okay, there are pin diodes at the front of these unit cells, and we have our circuitry to switch on and off these pin diodes connected with the power supply. Okay, so this is the design here. Okay, see, this is our biasing circuit. So we use this technique, and we were able to get the different frequencies, or we were able to switch the frequency based on the off and on state of the pin diodes. Okay, so here are some of the results for different samples. Okay, we can see that we can get frequency switching from one point to another point. So 9 until 9.5 gigahertz, we can get the frequency switching. And we can get a dynamic phase range here, which is around 250 degrees. So that was good enough for this type of design. So basically, we have shown that we can switch our frequency from one point to another point using pin diode with the unit cells. Okay, so these are the details of the results. I think I will skip this part. We can discuss later if there are someone interested in this part. Okay, then the next thing we did is the liquid crystal based design. So we use HFSS for simulation. So this is the simulation from HFSS. Okay, we have different types of elements: rectangular patch. We have the patch with a rectangular slot and patch with a circular slot. And then below that patch, we have a cavity for the liquid crystal. So right here, we filled the liquid crystal. Okay, and then it was on a dielectric substrate of Rogers. So we filled a liquid crystal right beneath the patch, and we know that we can have different voltage with the liquid crystal, and when we apply different voltage with to the liquid crystal, we can get different molecular orientation. So based on the molecular orientation, we can get different types of we can get different direct permittivities of the liquid crystal. So based on that, we can reconfigure, or we can move our frequency, resonant frequency, from one point to another point. So this is how we did the simulation and fabrication. So we fabricated different samples. Right. So we fabricated different samples as shown here. Okay. These are the samples, simple rectangular patch slots, rectangular and circular slots. And these are on the side, we have some stubs for the voltage. So, and then this is the cavity that we have made using Rogers right beneath the patch with the same size. Okay. And then we integrated both of them. We put it at the top, and we have a aluminum cavity to make sure that we have tightened all this thing. And then we fill liquid crystal under these patches using a syringe. So we have to make sure that we fill the liquid crystal very well. I mean, there should be no air gap, because if there is some air gap or air bubbles inside here, then the permittivity or the dielectric permittivity of the liquid crystal will be different, because it will mix with the air. So we have to make sure that there is no air gap in here. So we had to do it at multiple times. Okay, and okay, so this is the final unit cell that we have inserted inside the waveguide. So when we inserted this inside the waveguide and we applied different voltages, we got these results. Okay, at 0 volt, we got a frequency of 10.06 gigahertz, and we can move it from 10.06 to 9.88 gigahertz, which was good enough for this case. And this was based on simulation and measurements. So measured results gave us good response as well, almost same as the simulation. Of course, there are some errors here. We can see there is some difference in the reflection loss, but that was understandable because we are doing so many extra connections and unideal things here. So these were the results for the liquid crystal based designs, and we can see the phase. We can also move from one point to another point. So this is how we design reconfigurable unit cells for reflectarrays using liquid crystals. Okay, but one of the drawback or one of the problem with the liquid crystals is that it takes a lot of time. When we apply from 0 volt to 20 volt, actually the liquid crystal will change its permittivity from one point to another point. So I'm not exactly, I don't remember exactly, but from 2.2 to 1.4, the permittivity is varied. So when the permittivity is varied from 2.2 to 1.4 or from one point to another point, it is based on the molecular orientation. It is based on the variation of the molecular orientation. So that variation of the molecular orientation takes a lot of time. So in here we have shown that when we went from 0 to 4 volt, it took 105 seconds. So from 0 to 20 volt, if we see the extreme cases, it took 110 seconds. So between this result here, the green result and the black result, we have to wait for 110 seconds. Only then we can get the stable result like this. So that's the drawback of the liquid crystal. So when we want to use it for the reconfigurable antennas, we have to keep in mind that liquid crystal will take time to vary the frequency. So when we are having beam steering, the beam steering will be very slow. So we cannot use it for application where we need very fast beam steering. All right, so this is the summary. We got maximum tunability of up to 200 megahertz, which was good enough for our case. All right. So, okay, after the unit cell design, because we want to understand more about the unit cell design, so we have also done the equivalent circuit analysis, because as an electrical engineering students or researchers, we can understand more when we talk about electrical and electronic properties of this type of antennas. So this is a simple equivalent circuit model of a reflectarray antenna, which is based on a simple LC resonant tank with a resistance. Okay, and this is for this particular design. Okay, so for this particular design, we can calculate the values of this capacitance, inductance, and resistance by using these equations. So by using these equations, we calculated these values, and we use multisim to simulate this simple circuit with a vector network analyzer. Okay, and for pin diode, when we insert the pin diode, we have some extra capacitance and resistance here. So these are the circuits for pin diode based design and equations. So from there, we can see that when we do the simulation in multisim, we can get almost same or very close agreement between the results of CST and equivalent circuits. Okay, in both cases. So this is for the passive design and for the active design as well. When we turn on the diode and off the diode or without diode, we can get almost the same result. So from there, we can also vary different type of capacitance and resistance, and we can see how it will affect our results. So once we know that varying the capacitance, resistance, inductance, how it will affect our results, we can optimize our design based on different dielectric materials as well. Okay, so this is for the liquid crystal based designs. So we have a modification in the equivalent circuit, but we use the same technique, and we got almost the same result for the reflection loss and reflection phase curve for the liquid crystal based design as well. Okay, so once we are done with the unit cell design, the next step is to design the complete periodic array. So before we go into the complete periodic array, we have to understand, or we have to know that how we are going to place the elements in the array environment. So for that, we have to do some theoretical or mathematical modeling in MATLAB. So we did that in MATLAB. So based on the incident electric field, we know that it will have the scattered fields from the patch element, and it will have reflected field from the ground plane. So the total incident field will be dependent on the incident, reflected, and scattered field. So going into the more details, I will skip these details, but we use the details, and we did the mathematical modeling for the calculation of this phi n. Phi n is the phase response of the each element. So for the phase response of the each element, we did mathematical modeling in MATLAB, and we did it for different materials, and we can see that we can get the reflection phase curves like this. Okay, so from here we know how we are going to place the element in the array environment. So this is our array environment in the x direction and y direction, and this is the required phase from each element. So once we place our elements here, we need a phase like this. So different phases for different placement of the elements. So from here, we can design our array. So this is the design of the array in CST. Okay, so these are details of the design. So we use a horn antenna placed at a certain distance based on the f/d ratio, where f is the distance between feet and the array, and d is the maximum dimension of the array. So based on that, we design different arrays. And this is the surface current distribution and electric field distribution. So you can see the maximum surface currents are in the center as we decide for our array. And these are the results for the simple arrays. So for 12 by 12 arrays that we design, we can get a gain of around 20 dBs. So that was good enough for this design. But we see that as we increase the number of elements, we can get better results. We can get side lobes are reducing and our main lobe is improving. So based on our PC or our facilities available, we can see that if we have the facilities, we can design very big arrays and we can get better results. Okay, so these are the far field measurements of passive and active X-band reflectarray antennas. Okay, so based on the design that I showed earlier, we designed the reflectarrays and we did the measurements in an anechoic chamber. Okay, using feed horn and a standard transmitter here. Okay, so these were done at the JKES UTeM. Okay, and we can see that we can get very good agreement between simulated and measured radiation pattern results. Okay. And then similarly for the beam switching reflectarrays, we used the pin diodes with the array. So we designed the array, 36 element array just for the demonstration. And we used pin diodes on one half of the array. So on one side of the array, we use the pin diodes. So when we switch on the pin diodes, we can vary the reflection phase of that side of the diodes, and hence we can modify the beam. So these are the results. Okay, when we have 0 degrees, when we have all the pin diodes off, we can get the result at 0 degrees. Okay, and when we switch on one side, we can get our beam switch to plus 60 degrees, plus 6 and minus 6 degrees. So that was good enough for this design. This is only a 36 element design. That's why the side lobes are very high. But what we wanted to demonstrate is the beam switching based on the pin diodes based design. All right. So the next thing that we did is the millimeter wave beam steering reflectarray design. We designed at 26 gigahertz, okay, based on the mechanical rotation for 5G communications. Okay, so these are some of the elements that we investigated. So for 26 gigahertz, the dimension was 5.77 mm for the substrate, right? And then we did the fabrication similarly as I showed earlier. So I will not go into the details. Okay, and then measurements using a waveguide. So this waveguide we have also created, also designed ourselves, and we did the simulations, measurements similarly as I explained earlier. All right, so these are the fabricated unit cells up here, and these are the fabricated reflectarrays. So the reflectarrays are based on the mathematical model that we developed. And we use that mathematical model to develop these reflectarrays of 20 by 20 elements. Okay, so this is a feed horn, a very small feed horn at 26 gigahertz that we also designed here. So we placed the feed horn at the top of the array, and then this is our array, which is slightly tilted. So why we wanted to tilt this array? So that we can have a reflected beam that is not blocked by this feed horn. Okay, so this is the measurement setup that we used at UTeM. Okay, so this is the array here, which is tilted using a spacer for 20 degrees. So our reflected beam will be at 40 degrees without any blockage from horn or this structure here. Okay, so these are the results in azimuth and elevation plane. Okay, so elevation plane we were expecting at 0 degrees, so we got almost same at 0 degrees with a very good agreement with the simulation results. And for azimuth we got around 40 degrees as we were expecting. Okay, so these are for two different designs. Okay, so these are the cross polar and copolar. So we got a very good cross polar, which is less than, I think there was difference of more than minus 30 dBs. Okay, we got a maximum gain of around 26 dBs for this design. Okay, so this is showing the 3D for the copolar and cross polar. We can see very clear differences. Okay, so these are also the measure results. We can see our main beam. After the measurements, we can see the 3D main beam that is in the direction of 40 degrees, and there was very low side lobe levels. We got a very good main lobe level. Okay, as shown here as well. Okay, so for a frequency range of 24 to 28 degrees, we did the measurements, and we saw that as expected, as our per our design, we got the maximum gain at 26 gigahertz. But still from 24 to 28 gigahertz, we got quite acceptable gain for this type of array. Okay, and we got the maximum 3 dB beam width of 12 degrees and 17 degrees for different designs, and a bandwidth of 13.1 and 13.6%, which was good enough for this type of designs. Okay. So so that was for the passive design. So when we wanted to do the active design or mechanical steering for this design, what we did is we steered this beam from one angle to another angle. So for that, we have to make sure that our design is symmetric, and when we steer the reflect array here, it doesn't affect on the required phase of each of the elements. So it will affect slightly, but it will not affect too much on that. So for that, we did this type of different degree tilts at different degrees here, from 0 to 30 degrees, and we can see the surface current distribution like this. Okay, so that will give us a beam steering that I will show in the next few slides. Okay, so this is the copolar and cross polar. We can see quite clear difference here. And this is frequency that I showed earlier, frequency versus gain. Okay, so this is when we tilted, this is the simulated result. So we tilted from minus 30 to plus 30 degrees, and we expected to get the result at plus 60 and minus 60 for the reflected beam. So for the reflected beam, here we can see that we can get it from plus 60 to 0 degrees for one side. So similarly, we can get it for the other side as well. But for measurements, we did it for one side, but it is symmetric, so we will get almost same the results here. And for the azimuth plane, we can see that here, after we are doing the tilt, we are not getting too much difference. So that is what we were expecting. We were not going to disturb it in the azimuth plane. So this is how we get the result for the beam steering array. Okay, so for different angles, these are the 3D results. Okay, and frequency versus gain curve, we got a very stable gain. Okay, at different frequency for 0 degrees. And of course, when we want to tilt the arrays from our original design, it will affect on the gain. So it affected slightly on the gain, but still it was acceptable. And also the side lobe levels were good enough, very low. Okay, so that was all the sharing that I wanted to do for this different types of reflectarray design. So basically what we can conclude is that based on our optimization and our design, reflectarrays have the potential to replace the parabolic reflectors and phase arrays in many applications. Okay, and then as I mentioned earlier, we can use different types of techniques like electronic components. But when we use electronic components like varactor diodes, pin diodes, and MEMS switches, the beam steering will be very fast. We can get the fast beam steering. Of course, there are some disadvantages for those type of techniques, but when we use the phase arrays or mechanical beam steering, we will have to sacrifice our speed of the beam steering. So the beam steering will be slow in those things. Okay. And then this type of design we can also use for other planar surfaces like frequency selective surfaces, meta surfaces, and also the intelligent reflective surface. So the basic is same for all this, but we have slight modification for each of these. All right. So that's all from my side. So if you have any questions, please, you're welcome to ask.
Assalamu alaikum, sir.
Walaikum assalam.
Sir, it was a very impressive talk and it was very useful. Thanks. Thank you very much. I have a few questions.
Okay.
Please, could you mention can we use reflectarray for sensing application like any kind of sensing can we do with the help of reflectarray?
Okay, yes, of course we can use reflectarray for sensing applications, but depends on what type of application we are targeting. So as I mentioned, we need to have the beam steering for modern day application for sensing and other things. So for that, we need to know that can we use electronic components like pin diodes, or we use varactor diodes, or if we don't need the high speed beam steering, we can use simple mechanical rotation as well. So we can use it for the sensing applications.
Okay, thank you. And sir, what about the mutual coupling? Like because we analyze the unit cell and then we design full array using the same kind of unit cell. So mutual coupling is not any problem in such a scenario?
Okay, of course there is issues of mutual coupling. There are issues of mutual coupling, but we have to optimize that. Basically, when we design our unit cell, we design it in such a way that we can have optimum mutual coupling. So there are some techniques like we mentioned about slots. So when we use slot design, that means that the inter-element spacing between the two adjacent elements is similar, right? So we are doing the phase variation based on the slot dimension. So we are not moving, or we are not changing dimension of our patch. So that will help us to optimize the mutual coupling. So similarly, we have other techniques to improve the mutual coupling. But the mutual coupling in this case is not as much as for a microstrip patch antenna array. So this is slightly better in terms of mutual coupling, but there are issues that we have to address for this as well.
Okay. And sir, one more question. Like simulation is a big problem because I just started working on the transmit arrays and such kind of a structure. So I have HFSS 2016 and my computer RAM is around 64 GB, but still it cannot simulate the this kind of array. So what can I do for that? Like
yes, that's the problem. That's why we need to do analysis mostly on the unit cells. So once we are we are sure about our unit cell design, we can go for the whole array. So the transmit array design is almost similar to this reflectarray design as well, similar concept. So of course we need high-end PCs for that. We can't do it using simple computers. So we need to find, and also then we can also use some other techniques like we can use the hardware. There are other techniques we can do for the improvement for the simulation. but of course we need high-end PC for that.
Okay, okay. Like we cannot trust only on unit cell analysis because without designing full array, we cannot like expect the performance.
Yes, that's right. That's right. We, of course, finally we have to design the full array. Without the full array, we cannot finalize our design. But just basic is on the unit cell. But of course, we need high NPC for the simulations.
Okay, okay. Thank you very much, sir. Thank you. It was very impressive.
Thank you.
Hello.
Yes.
Thank you very much for this talk. Sir, I want to ask that we designed the unit cell for a normal incidence. But in a reflector array scenario, when we have a feed at certain distance, we can see that the waves are coming at certain angles. So can you discuss this, how we can fix this?
All right. Okay, so for that, as I mentioned, we need to do the progressive phase distribution. So when we place our unit cell or when we place our elements in the array environment, we have to make sure that the phase we include the incident and reflected phase angles. So that we had to do it. I mean, in our case, we did it using mathematical modeling and we did it MATLAB. So of course, we have to include that part. We cannot just base on the normal incidence.
Okay. And one more question, sir. You in the liquid crystal unit cell, you use some simulation in HFSS. So I want to ask about the material properties that you set in for the liquid crystal.
Okay, for liquid crystal that we use is K15 pneumatically liquid crystal. So we know the properties of that liquid crystal. So based on datasheet, when we have from 0 volt, what is the dielectric permittivity of that liquid crystal, and when we apply 20 volt, what is the dielectric permittivity. So basically, when we do the simulation, simply we just change the permittivity value in simulation. So we don't actually do it on the runtime. We simply change the permittivity value in the simulation and we get the results. Based on that data sheet, we need to know the type of liquid crystal and its properties.
Yeah, but I want to ask that, for example, if you have a dielectric block, so would that be the density of that would be like how you, because in a liquid crystal you have a liquid kind of situation, right? But in simulation, do you set it like a dielectric material or you include that?
Yes, it's a dielectric material. It's a liquid dielectric material, but in simulation we don't have option to mention if it is liquid or it's a solid. So it's just a dielectric material with different dielectric permittivities. So we just input the dielectric permittivity values only.
Okay.
Yep.
Thank you, sir. Thank you.
All right. Thank you. Okay, are there any other questions?
Dr. Inam, I want to ask you a question.
Yes, please.
Okay. When you do reflect array, normally we suffer in gain and bandwidth limitation. In your project on the crystal liquid, how you try to cater it? Something like summary for it.
Okay, the gain and bandwidth, of course, we have some disadvantages, but in the liquid crystal project, we didn't do the far field measurement. I mean, the full array design and addition measurements we didn't do. So we didn't discuss about the gain. But of course, the bandwidth we have to improve. That is based on our unit cell design. So we cannot change the properties of the liquid crystal, but we can still optimize the design itself. So if we use slot elements or we use a different type of design, we can improve the bandwidth and also some sort of gain. But of course, we cannot change the properties of the liquid crystal. So all the optimization and the improvement in the performance is based on our unit cell or the design of the reflect array itself.
Okay, that's all from me. Thank you.
All right, thank you, Mr. Hisham.
Sir, is there any limit for the F by D ratio? Like how much maximum we can take it, F by D ratio?
Okay, so there is no maximum limit, but based on the previous researches, in the optimum F by D ratio is like around 1. It is sometimes researchers use 0.9 and sometimes use 1.1, 1.2. But there is no, because we have to see if we use a very big F by D ratio, which means if we place our horn antenna very far away, then there will be spillover losses. Mean that the incident energy from our horn will be going to reflectarray, but there will be some of it, part of it that will be spilling over on the side. So that will extend the spillover loss. So that's why we have to keep it around 1. Sometimes we can use it 0.9 or 1.1, but it depends on our design as well.
Okay.
Right. Is there any more question from anyone?
Sir, have you any idea like how much maximum beam steering have been achieved using reflectarray?
It depends on the technique. So like I showed earlier, for the mechanical beam steering, we can get around 120 degrees. We got it in our results, 120 degrees with good stable gain. But if we are using the other techniques, we can get good beam steering as well by using the varactor diodes. So varactor diodes are like in the pin diode that we showed, we can only switch frequency. But in varactor diodes, we can get, we can vary the voltage and we can vary the capacitance of the diodes. So based on that, we can get a good beam steering as well using varactor diodes. But the maximum we can get with the mechanical rotation. So yeah, of course there are some disadvantages that it will be slow, but that's the thing that we need to optimize.
Okay. Thank you.
I want to ask a question. Okay, you mentioned about the similar concept methodology on frequency selective surface, metal surface, and intelligent reflective surface. What do you mean by that?
What I mean is that for those designed like frequency selective surface, intelligent reflective surfaces, transmit arrays, and things like that, we also have to do the two-step design. We have to do the optimization based on our unit cells, and then we have to go for the full periodic array design. So the basics of the design is same. Maybe there are some settings that we have to change, but the basic of the design and the concepts are almost similar to this, the reflectarray.
Okay, thank you. That's all.